Hello, and welcome to the Semi-Autonomous Land Management Project, also dubbed SALVO. My name is Bradley Masick. Additionally on the team, we have Randall Govan, who is the Navigation Systems Lead, John Henderson, who was the Chassis Lead, Jason Henry, who designed the failsafe system, Tyler Edge, who did the drive terrain, and Jonathan Aponte, who was the Land Management Lead. So what is SALVO? SALVO, as previously mentioned, is a semi-autonomous land management vehicle with a primary focus on mowing grass. The main goals at the outset of the project were to mow grass evenly, for the entire unit to be corrosion resistant, to protect users from flung objects or debris, for the electrical enclosure to be waterproofed, for the unit to have the ability to map the environment around it, a 1.5-hour operation time, a maximum speed of 3 miles an hour, and the ability to mow 3 acres, as well as having a remote fail-safe or shut-off system.
Successful development of this product meant that targeted end users such as average homeowners can save time by not having to mow their own lawn and money by purchasing a relatively cheap mower for the moderately sized lawn. Not only that, but robotic mowers are now a new niche market and the technologies and methods developed in this product can be used for further research. These research findings can be applied to future projects in senior design, and future iterations of SALVO can be also capable of hauling loads to prevent consumer from doing strenuous lifting during landscaping projects, improving the quality of life.
SALVO's control system uses a rather simplistic design. It receives feedback from rotary encoders based on the number of turns each wheel has completed, and that is used in a state system to transition through the vehicle states. The user starts the vehicle in the bottom left corner of the mowing area, where the initial move forward state completes the appropriate amount of wheel turns to reach the perimeter edge. Once there, make a 180-degree right turn, vehicle turn state, and repeat this until the end of the mow area is reached.
Our general test plans involved looking at the individual components as they arrived and testing those, and then integrating those into its respective subsystem and testing the subsystem as a whole. In this case, we were looking at the internal combustion engine in order to test its functionality and make sure that it meets the requirements of having 1.1 horsepower and 2.4 pounds of shearing force. We mounted the engine to the chassis during testing as it would be during operation, and then we turned it on and saw how fast it spun. Although simple, the blade compatibility test is aimed at ensuring the entire land management system can work as one cohesive unit and that the blade is attached securely. It should be noted that all of the equipment was pre-purchased and designed specifically for lawnmowers, which means that it can also be assumed that it will trim grass evenly and effectively, which is one of our main requirements. As we see on the right, there aren't many parts into this system, which means that it's also easily replaceable. All you have to do is unscrew that single bolt in the shaft and inspect the shaft or replace any parts. The wheel encoder integration test is aimed at ensuring communication between the rotary encoders and electric motors can happen properly. The reasoning behind this is that the rotary encoders are going to be used to measure the distance the vehicle has traveled through the number of rotations. As we see on the bottom left, the rotary encoders input data into the Arduino Mega, which inputs data into the Arduino Uno, and ultimately the motor controller to control the electric motors and change the vehicle state from going straight to stopping or turning.
The initial testing of the electric driving motors was performed while suspended to evaluate whether the tires were spinning in the correct orientation. This meant both wheels should be spinning in tandem when moving forward, and the left wheel would be spinning independently while the right is not during right turns, and vice versa for left turns. The movement pattern that was designed to be run while cutting was tested with a minibot to ensure the code was written properly. During the movement test, the 3D printed hubs failed due to shearing and was replaced later with metal pulleys that was welded to the hub. During the field test, the motor was loaded with team member weighing up to 120 pounds and showed no issues while in operation, so hauling could easily be attainable for this design concept. The velocity requirement was also met, reaching a speed of 3 miles per hour.
The navigation system was primarily tested via a mini SALVO prototype. This is where the base movement was outlined and the state system as well as their transitions were solidified. This mini prototype had many of the sensors we initially planned to use for SALVO in terms of object detection, such as ultrasonic to simulate LiDAR, wheel encoders, as well as perimeter wire sensor for defining the edge of the MO perimeter.
The largest problem that we ran into as a team was the simple cost of all the materials that were going to be needed for the project. We realized very early on that meeting the budget for this project was going to be extremely difficult with the task given at hand. Moving forward through that, the manufacturing, we ran into many delays when it came time to actually manufacture multiple components. This delay in the manufacturing also caused issues with the ability to test a lot of the codes. Not having the chassis constructed along with some of the hub components kind of led to a delay in testing some of the motors. Our advisor helped assist us in making some changes early on once we realized that the budget was going to be hard to meet. There was a discussion with our advisor in changing something in regards to the motor that would actually power the land management system. Early on, it was looked at doing that with an electric motor. And when we discussed some of our issues in terms of budget with the advisor, they led us down the road of looking at the potential option of using an internal combustion engine, which in turn turned out to be a better option in terms of budget. So it led us in a great direction that way. Also, when we started running into manufacturing delays, they led us down the path of what the best manufacturing processes would be and also assist in manufacturing a few of the components themselves.
The biggest takeaway from this experience was learning how to adapt and be flexible. Engineering projects are very complex and many problems can arise throughout the process. As a team, we had to learn how to adapt our design based off of what was available. For example, we were only able to cut an aluminum chassis, which therefore altered the way we attached other components. We had to find quick workarounds while still maintaining the integrity of our project. We also had to switch critical portions of our design, such as a blade engine from an electric to an internal combustion engine, in order to stay on budget. This meant that the project would be delayed and new analysis would need to be carried out. That said, it was necessary to make these changes so that the project would be completed. Without those design changes and the flexibility of the team, SALVO would not have been developed as far as it did. At first, these online platforms took some getting used to, but within a couple of months, we were able to work cohesively. Collaborating in this setting meant we were each responsible for our own work and generating our own ideas. We would come together in an online meeting to share and discuss these ideas, similar to how it would be in person. We would upload our work into shared folders so that all would have access to them at any time.